All right, section 3, we're going to look at increasing, decreasing functions in the first derivative test. So increasing and decreasing functions is stuff that we have seen before, but we have to go ahead and do it a little differently than we did in pre-calc and other classes where we kind of use the graph mostly in graphing utilities. We're actually going to try to do this with just using calculus and without the aid of graphing utilities. Now we can obviously keep checking our work with our graphing calculators, but obviously we want to make sure that we can actually do this with the calculus. So for an increasing function, the official definition is going to be this. We say a function is increasing in an interval, and we'll call AB, if and only if f of A is smaller than f of B for all A and B in the interval. So if we'll call A sub I and B sub I. So these are all basically just points in the interval. So if I make my little graph, let's say I draw a function that looks like this. So if I pick 2 points, so let's say this is my A and this is my B here. And obviously it increases in other points, but I know it's increasing in this interval because no matter what point I pick, so I pick this point here and then I pick this point here, the y values are getting bigger. The y value on the right one is bigger than the y value on the left one. So that is going to entail that it is increasing, assuming that our a sub I is less than our b sub I. So that is going to be what we see for an increasing function. I mean, obviously you can kind of see that an increasing function is going up. And I mean, if we think about this one, this graph is really going up in a lot of different ways. But that's the idea. And a decreasing function is going to be just the opposite, right? So we say a function is decreasing in an interval. And we'll use different ones. So an interval CD, if and only if f of C sub I is greater than f of D sub I for all C sub I less than D sub I in the interval. So as long as the y values are going down, so the one on the left is bigger than the one on the right, then we say it's decreasing. So if we look at our graph here, so like it's decreasing from here to here for sure. So if this is our C sub I and this is our D sub I, you can see that the functional value is bigger on the left one and not the right one. That's what's going to kind of make it go down. So this is fine, and with a graph you can kind of see when it's going up and down, but what we're going to try to do is we are going to try to come up with a test for increasing, decreasing functions using the derivative. And so here is the basic idea of how this works and why it works and how we can do it. So let's look at a function. This is going to be a proof by demonstration. I'm not going to prove this, rigidly, but let's say we have something like this. Let's just say it comes. Let's just do like this. Well, that's terrible. Let's try again. So let's go like this. So I think we can agree in this region the graph is increasing. So the idea is if I look at the tangent line and points in that region. So if I look at this tangent line, here's the tangent line at that point. If I look at the tangent line here, it is there. If I look at the tangent line there, it's there. What you notice about all these tangent lines in this region is that they have a positive slope. They have a positive slope. So if we think about it, what we can kind of just denote from this is that the tangent lines, and we'll summarize that here in a second, tangent lines have a positive slope when increasing. And if we look when it's decreasing, not surprisingly, we kind of see the opposite, right? So if I look at a point here in that decreasing region, that tangent line is going down, and this tangent line has a negative slope. This tangent line has a negative slope, because in these regions, I think we can agree the graph is going down. So these all have a negative slope. So we say the tangent lines have a negative slope when decreasing. Well, we can put this into calculus because if you recall, the derivative is how we find the slope of the tangent line. So if your derivative is positive, we have an increasing function. So if f prime of x is greater than 0 in an interval, then it's increasing. Then the function is increasing. And just the opposite is also true, since the derivative is the slope of the tangent line. If f prime of x is less than 0 in an interval, then the function is decreasing. So sometimes it's going up, sometimes it's going down, but all we had to really do is just really find the derivative, find when it's positive, find when it's negative. Now, obviously, I did not say when it's 0, because when the derivative is 0, that means we have a horizontal tangent line. I've got a lot of lines going on over here. But the derivative is going to be 0 at these maximum and minimum points, so like here and here, because you have a horizontal tangent line. So it's not really increasing or decreasing at that point. It's just kind of the in-between point, and that'll be important here in a little bit. So you can actually take a function and figure out when it's bigger than 0, when it's smaller than 0, and we obviously want to also know when it is equal to 0 to kind of see where it changes. Sometimes we use what's called a sine chart to do that, and so we'll do some examples to see how that works. So in this case, it says, what intervals are the polynomials increasing and decreasing? And then we could, of course, check this with the graphing calculator. So we know it's increasing when the derivative is positive, decreasing when the derivative is negative. So the first thing I'm going to probably find is the derivative. So f prime of x is going to be x squared, because we bring the 3 down. 3 times 1/3 is 1, 1 less power, plus 4x, because we can bring the 2 down, minus 5. So we want to know, when is this positive, when is this negative? So the first thing to do is we're going to first figure out where is f prime of x equal to 0, because that's going to be where it changes, because on one side is probably going to be positive, one side is going to be negative. So we will figure out where is 0 equal to x squared plus 4x minus 5. And now this is really the hardest part about this section, is because you have to remember how to solve equations from previous coursework. This is a quadratic, so nothing crazy. I could factor it, get x plus 5, x minus 1. And so then if I solve those for 0, I get negative 5 and positive 1. So the derivative is 0 at negative 5 and positive 1. So now if I want to check this, if I want to see where it's positive and negative, I use a sine chart. So now that I found what's 0, I make a sine chart. And if you've never made a sine chart before for like a quadratic inequality, it's not super difficult, but if you've never done it before, it's a little different. So I'm going to make a number line, and I'm going to put those two values on the number line, negative 5 and 1. So this is going to break the number line into 3 parts. So the first part is all the numbers smaller than negative 5. So we'll say negative infinity to negative 5. The middle part is going to be points in between negative 5 and 1. And then the right side is going to be points that are greater than 1, or 1 to infinity. So what I'm going to do is I'm going to pick a point in each of these regions. We're going to call this a test point. So in this region, I'm going to pick negative 10. And in this region, I'm going to pick 0. In this region, I'm going to pick 10. You could pick any point that's in those regions. So any point smaller than -5, any point greater than, or between -5 and 1, any point bigger than 1. And what I'm going to do with those is I'm going to plug those into the derivative, and all I care about is if it's negative or positive. So my derivative is here, so I'm going to plug in -10 and see if I get a positive or negative value. I don't really care what I get, I just care if it's negative or positive. So if I plug in -10 squared plus 4 times -10 minus 5 is 100 minus 40 minus 5. That's 55, but I don't really care. All I care about is it's positive. All I care about is the sign. That's why we call this a sine chart. If I plug in 0, 0 is really easy because I get 0 squared plus 4 times 0 minus 5. So that is negative. And then if I plug in 10 squared plus 4 times 10 minus 5, that's definitely positive. It's 100 plus 40 minus 5, so that's positive. Now, what we know now, we have this sine chart, is anywhere where the derivative is positive, the function is increasing. So it's increasing here and it's increasing here. And anywhere the function is negative, the derivative is negative, it is decreasing. So we can tell right away for this function, so it's increasing between -infinity and -5, and then between 1 and infinity, and it's decreasing on the interval -5 to 1. So using that sine chart, really easy way to see this. Now we could graph it. I don't want to graph them all. We'll graph the next one. But if you graph it, go ahead and graph it yourself. Hit pause on your video. Check. Make sure that it really is increasing on these intervals and decreasing between them. And if you use Desmos or something like that, you can see where these points are, that it changes at this -5 and this 1. All right, so let's look at this next one. So we have y equals x squared minus x to the 4th. So again, first thing we're going to want to do is take the derivative. So dy dx is going to be 2x minus 4x squared. And again, that's, or 4x cubed, pardon me. That's just taking the derivative out like we normally do. So the tricky thing about this one now is we want to figure out what the critical values are. We want to know where the derivative equals 0. Using a little different notation here just because we had the function in y and not f of x. So we're trying to figure out when 2x squared minus 4x cubed equals 0. So the easiest way, I think, is to take a 2x out so I can factor that out of the problem. And so I'm left with 2x times 1 minus 2x squared. And so I also want to talk about this factor and this factor now. So now if I take 2x and set it equal to 0, x is certainly 0. If I take 1 minus 2x squared equal to 0, a little trickier, I'll add 2x squared to both sides. I'll divide by 2. So x is going to be plus or minus the square root of 1/2. Because remember, when you take your square root, you're going to have the plus or minus. So this is the we have 3 critical values now. We have 0 and plus and minus 1/2, radical 1/2. Now the square root of 1/2 is the same as the square root of 2 over 2, so it's about 0.7. So that'll kind of help us when we talk about our sine chart. So I know we have 0 on there. I know we have positive square root of 1/2. And I know we have negative square root of 1/2. So this region over here will be -infinity to negative square root 1/2. So that's that first region. So if I pick a value smaller than the square root of -1/2, we'll say -1. This is between negative radical 1/2 and 0. So because that's like 0.7, we'll do like -0.5. Not a real clear one in this case because It's kind of jammed in there. So this one is going to be between 0 and radical 1 over 2. And so I'll just do positive 0.5. And then we have positive radical 1/2 to infinity. And so we'll just use 1. So these are my test points. So remember, then I want to figure out what's the derivative at those points. So I want to know is the derivative positive or negative. So f prime of the test point. So if I plug in -1 to my derivative, so I get 2 times -1 minus 4 times -1 cubed. So that's going to be -2, and that's going to be plus 4, which is going to be 2. So in this region, it's positive, so the function should be increasing. Now if I do -1/2, I get 2 times -0.5 minus 4 times -0.5 cubed. So this is going to be -1 plus 1/2, because 1/2 to the third is going to be 1/8, so you get positive 1/2. So that's going to be negative. So this is going to be negative, so it's decreasing. And you can just put these in the calculator. You don't necessarily have to work them out by hand. So if I put in 0.5, so 2 times 0.5 minus 4 times 0.5 cubed. So that's going to be 1, and that's going to be minus 1/2. So that's going to be positive. So in this region, it's going up. And then if I put in 1, 2 times 1 minus 4 times 1 to the third, that's definitely going to be negative. -2, but it doesn't really matter. It's negative. So it's negative, so it's decreasing. So I have 2 regions of increase and 2 regions of decrease. It is increasing on that first interval, -infinity to negative square root of 1/2. And then it's increasing again from the square root of, from 0 to positive square root of 1/2. It is decreasing on those other 2 intervals. So it's decreasing negative radical 1/2 to 0, union radical 1/2 to infinity. So let's go ahead and let's see if it actually matches up with the graph shows. So I'm just going to graph my original function and see if it matches. So here's the graph that I kind of pulled off of Desmos. So you can see that it is increasing. It definitely looks like it is increasing from -infinity till we get to this weird point here, -0.707. But if you put square root of 1/2, then that is going to give you 0.707. So if you do the negatives, that will be the negative. And then it kind of will decrease again. Then it increases from 0 to positive that. And so you can see that this graph really is agreeing with what our sine chart says. So we always like when it agrees with what we said. So everything seems to match up, that the increasing are increasing and the decreasing are decreasing. The second thing we're going to look at in this section is what's called the first derivative test. Now the first derivative test is going to be a way to help find the maximums and minimums in a region. So the first derivative test says this. It says if a function changes from increasing to decreasing, then it does so at a maximum point. So if I have a function so it's going up and then it goes down and then it goes up. So if it changes from increasing to decreasing, so it's going up and then it changes at this point going down, then that has to be a maximum point. So that is half of the first derivative test. The opposite is also true. that if it changes from decreasing to increasing, so down here in this interval, so it's going from decreasing and then it starts to increase, then it does so at a min. And then we can discuss if that minimum is a relative minimum or an absolute minimum or maximum, but in general, that is going to be the idea. So if it goes from increasing to decreasing, it's at a max, and if it's decreasing to increasing, it's at a min. So that same sine chart we made is going to show us where you can kind of change between increasing and decreasing to see if it's a max or a min. And so that's the essence of the first derivative test. So we'll look at a couple examples of different functions that do this. So this says find the first derivative test to find any extrema. And extrema is just a fancy word for mins and maxes. And find the intervals where it's increasing and decreasing. So if this is my function, f of x, I know it says y, but I'm just going to change to f of x. Then f prime is going to be negative 15x squared plus 2x plus 1, and then the negative 7 goes away. So the first thing I'll do is I'll find when this is 0. When negative 15x squared plus 2x plus 1 equals 0. Now, generally, these things will factor, and you could actually factor this. What I would do first is I would divide everything by negative 1, because when I'm factoring, I like that leading term with the x squared to be positive. And so when I factor, so we'll have to figure out which values go where. So if I have 5x and 3x there, so I'm trying to get to FOIL to negative 2, so I believe it is negative 1 and positive 1. So because I have negative 5 and positive 3. So you could also do quadratic formula. However you want to solve this is fine. But this is just your general quadratic that's going to have zeros at negative 1/5 and 1/3. So those are going to be my extreme values where the derivative equals 0. Now, it's important to know that these are points. These are points that make the derivative 0. Because we will have other points where it will change from increasing to decreasing, but it has to be at a point. So if I do my sine chart, so my points are negative 1/5 and 1/3. So not a lot of regions, not a lot of area to plug things in here. So I have my region negative infinity to negative 1/5, negative 1/5 to 1/3, and then 1/3 to infinity. So I'm going to try to pick a test point in each of those regions, just like we did on the previous. So I'm going to pick a test point, and then I'm going to figure out if the derivative of the test point is negative or positive. So I'll do negative 1, I can do 0, and I can do 1. Real easy. And I will plug them into here. So if I plug in negative 1, so I get negative 15 minus 2 plus 1. So that is going to give me a negative, so it's going to be decreasing. At 0, it's going to be 0 plus 1, which is positive, so it's increasing. And then at 1, I get negative 15 plus 2 plus 1, which is negative 12, which is negative, so it's decreasing. So we're increasing only from negative 1/5 to 1/3, and we're decreasing on the other two intervals. That would be negative infinity to negative 1/5, union 1/3 to infinity. So remember, if we're going down and then we go up, it's going to be at a min. So we know there is going to be a min at x equal negative 1/5. And if we're increasing and then we go to decreasing, like we do at 1/3, that's going to create a max. So there's going to be a max at x equal to 1/3. Now, if you wanted to figure out what those are, we could just simply plug those x values into our original function, and that would give us our y value. You can, of course, also check this on Desmos like we did the other one. We won't check this one. We'll check the next one just to kind of show that that is the max and that is where the min occurs. So this next one is pretty bizarre because it is 4 over 3x. So we have to figure out where the derivative is 0. And this one's going to have a new wrinkle to it. So if I call it f of x equal 4 thirds x to the minus 1, because again, when I'm going to take the derivative, I'm going to need to make sure I have it as an x to a power. So f prime of x is going to be equal negative 4 over 3 x to the minus 2, because I'm bringing that negative 1 down, and then 1 less power. So if I rewrite it, f prime of x is going to be negative 4 over 3x squared. So when I do my sine chart, I have to figure out when this derivative is going to be 0. Well, this derivative, f prime of x, is never 0. Because if I had negative 4 divided by anything, I'm never going to get 0. But the derivative is undefined at x equal to 0. Because if I put a 0 in the derivative, negative 4 divided by 0 is undefined. So at undefined values, you can sometimes get changes from increasing to decreasing. You won't get a max or a min point, but you could get a change from increasing and decreasing. So I will put a 0 as my only critical value, but I'm going to put a little u above it, because what that's going to tell me is, yeah, that is something that could change the increasing, decreasing, but it's at an undefined value. So I have these two regions, and so I'll plug a test point in, so maybe negative 1 and maybe 1. So my derivative at those points, if I plug those in, if I plug in negative 1, negative 4 over 3 times, it's just 3, so it's going to be negative, so it's decreasing. And then if I plug in 1, I also get a negative, so it's still decreasing. So the intervals of decrease for this function is going to decrease from negative infinity to 0, and then again 0 to infinity. Now I did have to exclude that one value. I cannot have 0 as a value because it is undefined. So I can't have that as an increase or decrease. It has to be taken out. And so since this thing is always decreasing, that means there is no max or min. So if I bring in a graph of this, so here is the graph of this I graphed. So what you can see here is you can see that it really is constantly decreasing. So it's going down ever so slightly, and then at 0 it has that jump, and it goes up here, right? So that jump, what makes it undefined, typically makes those vertical asymptotes like we talked about way back in chapter 2. So you can kind of picture this having that asymptote at that value. Now this doesn't mean that it doesn't always change from increasing to decreasing. It certainly could. If the left side looked the same and this side looked like this, well then on the right side it's increasing and the left it's decreasing. So it can change at those undefined values. That's why we always do check them, even if there is nothing that makes the derivative equal to 0. All right, so let's go ahead and look at our last one. Our last one is Xlnx. So kind of a tricky one because a couple things. We have a derivative that's going to be a product rule for this f of x. So remember product rule, f prime g plus g prime f. So the derivative of this guy, f prime of x, is going to be the derivative of the first, which is the derivative of x, which is 1, times ln x, plus the derivative of ln x is always 1 over x, times x, which is the first function. So this simplifies out a little bit to ln x plus 1. And so we're going to want to figure out where that equals 0. So again, this, we had quadratic solving. Now this is going to go back and kind of review our exponential solving. So to get x by itself, I'll subtract 1 to both sides, and then I'll switch to exponential form. So remember, ln has a base of e. So our value that's going to make this 0 is e to the negative 1 equals x. And if I want to write it a little simpler, it's 1 over e. Because for exponential form, we take the base to whatever's over here equal to whatever's in our log parenthesis. Now, a couple issues with that. First of all, I have no clue what 1 divided by e is. So if I put that in the calculator, this is somewhere pretty close to 0.367. So in our sine chart, I only have that one critical value, and it is at 0.367, which is 1 over e. So when I list it formula, I'll probably use the 1 over e. But a bigger issue as well is this has an endpoint. This function is only defined until 0. So the log functions can only be positive. So there is no graph to the left of 0. So if you have a square root function, which is 0 and bigger, or a log function, which is 0 or bigger, we don't want to say it's decreasing always or increasing always, because a lot of part there's no graph. So I'm going to pick some test points for this. So my regions of increase, decrease are going to be 0 to 1 over e, and then 1 over e to infinity. And they both can be increased, they both can be decreased, or more likely one of each. So I'm going to do a test point. Maybe I'll do 0.25. And then I will do, I don't know, we'll do 1. So when I plug in the derivative, the test point at the derivative, we'll see what we get. So for 0.25, I will do ln of 0.25 plus 1, which I'm just going to plug it in the calculator, and I get about negative, I don't care, 0.3, blah, blah, blah. So it's negative, so it's decreasing to start with. So it's decreasing from 0 to this 1 over e. And then it is going to, I'm assuming, increase. So if we do the ln of 1 plus 1, well, the ln of 1 is just 0, so this is just 1, so this is positive, so this is going to increase. Now, this is at a point, so no problems with asymptotes here. This is actually something that makes it 0. Typically, you get the asymptotes or undefined things when you have things that are divided by 0. We didn't have that in this case, so all we have is just these values. And so what I can say, I can conclude a lot from this sine chart. And then we'll look at the graph, make sure it kind of works for us. So this thing decreases from 0 to 1 over e. It increases from 1 over e to infinity. And so at that point, since it's going from going down to going up, that is going to make a minimum. So there's a minimum point at 1 over e. So I discerned all that information just from getting the derivative and making this sine chart. Now, I think the trickiest thing for this one certainly was you had to know that the domain of a log function starts at 0. And so I'll go ahead and pull up a graph of this and we can see how it looks. So here's our graph. So you can kind of see this. So it goes from decreasing to increasing at that 0.38. Which if I look at what 1 over e was, it was 0.367, same thing. So that kind of verifies what we see. It shows you when it's decreasing, when it's increasing. Again, the trick of most of these is knowing domain, or there's always some kind of derivative trick to make them work. So that's a little bit about the first derivative test, about making sine charts. Obviously, if you have questions, let me know, and we'll go from there.